Раз, 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 отлично. Сейчас подождем, пока все не заинтересованные в криптографии выбегут из зала, чтобы они не шумели, не толпились, и мы начнем. Ну, в принципе, пока можно о себе. Меня зовут Олег, я представляю здесь группу исследователей из Томского государственного.
I'm Oleg. I'm from Tomsk State University. We shall talk about crypto, but this will be a very light talk. Even if you've never heard about crypto, you will understand everything. So we'll be talking about white box crypto. I think everybody knows what contexts are. So a black box, a well-known phenomenon, right? You know the inputs, you know the outputs, and this is what you have to study. You know nothing about the underlying algo. All you see is plain text and encrypted text. In a gray box, you have some information about the keys. You might know side channels, for example, or timing attacks, or electromagnetic pattern. So some information is available. In a white box is a setup where the attacker has access to the executable code. He can easily, or they can easily, transform the inputs, for example, or play with the outputs. Please know that traditional white box crypto cannot be considered safe or secure because we do not observe here the Kirchhoff principle. Well, for example, you might want to have a DRM system. Say you're trying to buy premium content. Well, it may well be that you want to buy the new episode of Game of Thrones in Super HD quality. So you have a client application that will decrypt DRM protected content that has been encrypted. Well, the problem is that you're running this application on your own computer, and if it's a bad user, actually, he can use dpro to actually extract the content and start selling it. Yes, the owners of this service will hate to see that. Or take a web application that you want to protect as a security administrator, and this application sends a particular parameter to the server, and a bad user can actually launch a group seed and start doing SQL injections, morphing the inputs. So we can use white box crypto, and data will be transmitted encrypted, so it will be more difficult to mangle it. So the idea is that you take a particular encryption, you take input data, it could be a key, not necessarily an algorithm key, by the way, and that shows, and what you get in the end is the image in the right hand part of the slide. That way you sort of embed the key into the cipher. And you do it in a manner that would assure that reconstruction of the key will be very difficult. This is the main idea of white box cryptography. There are already available white box implementations. Well, it's a regular advanced encryption standard AES. Now, if you don't remember how AES works, this is a crypt sheet for you. So add round key, bit by bit. Then you use a table to substitute bytes. Then you do mixed columns. You actually shift the columns. All these are linear procedures. You can easily do field multiplication in tables. And this was noted by Cho et al. So what Cho did was a simplification of AES to the level of tables and column shifts alone. Well, and they say that in order to reverse this stuff, you need 2 to the power of 30 operations, so they also propose strengthening it with input and output coding. So this was my short introduction into white box cryptography. If you need more details, please follow the link over there. Now the stuff we propose is key hashes. So you have the same server application that's using some IDs that we want to protect. Rather than encrypting everything, for example, if we work at the WAF level, decrypting could actually be a bad idea because it consumes too many resources. So we can add hash, but we can't use the regular hash because the attacker will also be able to access this hash. So we need key hashes. And we need either a block cipher here or a particular schemas. It could be HMAC, for example. Shown below is the regular hash computation approach. So you hash everything block by block, then you combine it all and you get the hash value. Well, HMAC works in a different manner. You actually XOR the hash key with different values several times. It's well known that hashes can be updated. They have internal values. So if you start computing it, you can do an update, and that way you'll get the same result as if you were hashing the whole string. So here I'm underlying XORed keys with OPADs. According to the standard, they should have the length of 1 hash block. This way we have 2 key blocks that will always sit in the first hash block. Well, that way we can take the usual hash implementation and XOR our key and remember the state. Then we use a different constant on XOR and we get another state. Then we save both states. And then we can take these states and enter them in a hash calculation formula. So we'll hash the message with the first one, and for finalization purposes, we'll use the second state and we'll hash again. So this way, we don't have the key, but we do have 2 states. And these are essentially 2 values of the hash function on a block of text with length of 1. Which means that the hash itself is not shown clearly in the algorithm anywhere. We have actually tested it on a number of NIST, RFC and other vectors. It's based on SHA 256, and we've also done it on AS 128 and CDR mode. That's it. I'm sure you've already taken a photo of the repository, so if you have any questions, fire away. Now the way I get it, you have these 2 blocks, key plus external and key plus internal padding. You do the pre-computing and based on that you will calculate the hash. Anybody who has these 2 blocks can calculate the hash. Sure. What we're trying to do here is protect the key. Sure. And the perp can actually use the same function to calculate the hash. What's the profit then? Well, for example, if you develop an exploit on Go or Python, it will be difficult for you to call JavaScript code. Again, if you've compiled and obfuscated this stuff, it will be difficult for you to execute JavaScript. And I think we can have a protracted argument about whether it makes a lot of sense or not. Is it correct then that the white box nature of HMAC is based on the sheer fact that you transform the case into two states? That's right. Followed by a regular code, the regular hash. That's right. You can obfuscate it if you want to. And was it a part of some other research? Was it your thesis or something? Well, it was part of our annual research, so we did it just for kicks. So my question is also about white box HMAC. So you XOR the keys with internal and external padding, and then you save the states, that's right? External and internal padding are constants, that's right? Published ones. What makes storage of a XORed state different from storage of an open key itself? No, we don't store the key. We store the hash. It's not the full hash, it's just the first block of the hash. That's right. So we simply hash it, and we take the output of the hashing function. So if I want to do, say, a length extension, I will be able to do that. Well, the only thing you do is that it will be difficult for you to reverse it. That's right. We have other speakers in the same fast track, so let's call it a day for the gentleman.